Yes, I'm here to talk to you about Linux Userland rootkits, which is kind of a topic people often kind of ignore because they're not as fun and interesting as kernel rootkits, I guess. But who am I? That's just the generic who am I slide. I'm Darren. I'm here to talk to you about Linux rootkits that are based on LD preload. So I'll just get into it. So there's a whole category of Linux userland rootkits that are ring 3, they run user mode, they don't touch the kernel, they're not like kernel space rootkits, and they're all based on LD preload. So what LD preload is, it's an environmental variable interpreted by the dynamic linker that tells the preload library ahead of loading other libraries. So it's like you change the search order, so when a program is going to look for like a function like string copy or whatever, it'll take one from our preloaded library instead of taking one from like the libc or whatever. So it's used in debugging and it's used for function hooking, and it just allows you to basically replace functions at runtime. So it can be set globally across the entire system by using etc ld.so preload file. You just put the path to your hook library in there, and then every program on the computer will load that instead of load the real libc. On OS X, you've got dild insert libraries. On Windows, you can allegedly do this with AppNet DLLs, but that breaks fucking everything. Your Windows machine just stops working if you start pissing about with that. And I know that the BSDs also have a similar thing. So this is like, it's a fairly generic technique to preload your code in ahead of the legit code. So how this relates to rootkits is if we can replace functions at runtime, we just have like an extremely simple generic way to implement hooks. So we can modify the behavior of programs, we can tell programs to lie, or we can lie to programs, and we can hide stuff, like we can hide files, we can hide processes, we can hide directories. On Linux anyways, everything's a file, so like just by implementing some basic file hiding, we can hide stuff from the rest of the system. It's a super powerful technique for debugging because, like, you can patch out things without having to like open up a binary in IDA and actually patch it. You can just replace the library call. So these rootkits are actually really common, but everyone ignores them because they're not as sexy as like kernel rootkits or whatever. And so I thought I'd make a quick list of like the pros and cons. I'm not going to read them all out, but the pros are basically: user space preload rootkits are more stable, easier to write, quicker to develop, and they don't fucking break all the time, unlike kernel rootkits. If you've ever tried to write a loadable kernel module rootkit for Linux that runs in kernel mode, and you've tried keep it running across like 2 or 3 different kernel versions, you will have torn your hair out by having this massive if-defs, because the ABI for the kernel ABI in Linux is not considered stable. It can change at any time, they add new shit, they change shit. So instead, targeting user mode, you get a very stable ABI. Some of the rules in Linux development is that they don't break user space. They're also not usually architecture specific, so you don't have to do any shit in assembly. You can just write the stuff in C, quite high level, boom, it works. Easy to expand, you can customize to the target. However, on the downside, they're vulnerable to timing attacks. They're vulnerable to just compiling a binary statically, makes it invulnerable to this rootkit technique. So just adding the -static flag to your compiling of like whatever you're doing means that the rootkit no longer affects it. You do need to have a dev or a build environment that's almost identical to the system you're targeting. They're vulnerable to stuff like timing attacks, so because they interpose themselves, they go in between like the legit function call and like your hook acts in the middle and adds extra clock cycles, so if it does like a comparison, it does cause a timing thing, and I'll show you that in a minute. It's also vulnerable to just running LDD in a loop. Sometimes will cause things to break and show the hidden stuff when it's not supposed to. So I'm going to give you a quick crash course on how to write one of these. So what you have to do is you find a function that you want to hook by using strace, usually, or GDB. You go, what am I trying to hide from? So then you think to yourself, how am I going to hide it? Like, what do I need to change to hide my stuff? You write the hook for that function, then you repeat for the other like 30 functions you're going to need to hook to, get any stealth. So we're just going to go straight into some examples. And I really hope the code on screen is actually readable. I spent a while trying to make it readable, but... So here we have a simple hook that just breaks the rand call by forcing it to return 42 each time. So if we compile that as a library, and we have a second program that just, generates a random number. And then if we preload in our hook, every call to rand now returns 42, because we're now calling this rand function instead of the legit rand function. So that's like the most basic, simple example of how these work. Now you can imagine doing that globally to every function you can think of. So sometimes we don't just want to fuck up the random number generator. Sometimes we want like a check or a condition. So we start adding conditionals in. So this is a slightly more complex example, and all it does is it DL opens the real libc path, which is hard-coded, and it defines the rand from that as old rand, and then if an environmental variable is set, it'll return the real random, otherwise it'll return 42. So this is like a basic control flow check. So what you do is, when we test it with like hex equals lol, which is like, please use the real random, don't cripple the system, we get real random numbers, but when we don't have that set, we're getting broken random numbers. The same logic can be applied to pretty much any other function hook you want to implement. So we can then go and add more conditions, like create input-output filters. So I decided to use this example for readdir. This is like the most basic example of hiding files. This is like an actual proper thing that you'd want your rootkit to do. So we've got a file name hide_me, and we want to hide any file that's named hide_me, or has the string hide_me in its file path. So what we do is we define the original readdir, and then we have if the string hide_me is in the output of readdir, don't return, otherwise return everything's fine. Pretty straightforward. This is what the output looks like. So when we run ls without the hook installed, we get files. And then when we run ls with the hook installed, it's hidden hide_me.so and hide_me.c because they've matched the please hide this shit condition. So that way you can hide your malware binaries all across the system. Sysadmins can't see it when they do cd and ls around the place. It's a pretty straightforward but pretty powerful technique. And also some EDR software is dynamically linked, so it'll hide from those too. Good job. So this is also where I'm going to show you the timing attack that I came up with. And this is where it gets really neat. So because we've got all the shit that we're doing in the middle of the string comparison, that takes up extra clock cycles, that takes up extra processing time, and that makes everything slower. So our hooked example is going to run slower than our legit one. So when we check with time, we actually notice there's a measurable difference in the timing. So with the hook installed, it's taking 0.003, whereas normally it's taking 0.002, which it doesn't seem that big a deal, but that's actually quite a huge difference in performance. That's it's like 50% slower or something. So that kind of performance impact applied across the entire system as opposed to one just tiny example here can be quite serious, and you start noticing that everything's slow. So another fun thing we can do is, because with preload kits, we're globally hooking everything. If we've them installed in etc.ldso.preload, we can implement really trivial local backdoors to allow unprivileged users to gain root. So the most common technique across all the rootkit examples that I found in the wild for this was to simply use an environmental variable check like we used previously in our hook for random. So what we do is, if that envar is there, and if say we're trying to run a setuid binary or something, it'll check, is the magic string present? If so, drop a root shell instead of doing whatever else. So this is an example mostly stolen from the Jinx 2 rootkit, which has been extremely widely used in the wild. And what it does is it checks if an environmental variable is set, and if that's set, and if the current EUID of the process calling it is 0, i.e. root, it'll spawn a shell. Then what you do is you stick that hook inside every other hook, which is kind of a bit of a lazy way of doing it, but that's how it works in Jinx. So for example, the access hook, you've got this call that drops to a shell if env set. So every time a program calls access, not only will it check if access has some other hooks, but also it'll do a check to see if the environmental variable is set and spawn a root shell if so. So it's a pretty decently powerful technique for rootkitting boxes. And this is how it looks when we test that example out. We when we run who am I over user, then if we set the environmental variable, in this case, hats, and we run the gpasswd binary, which is setuid root, it'll trigger the getEnv hook, and then we get a root shell, and yay. The other thing that's quite common with these is to implement various kinds of remote backdoors to allow you to regain access to the system that you've installed when after it's compromised. And what's interesting is that a lot of them all use the same, approximately the same kind of remote backdoors. Like everything based on Jinx uses an accept hook. That seems to just be like the de facto standard. And then you've got another whole family of them which seem to hook PAM instead. PAM is the pluggable authentication modules that handles like login authentication on Linux. And by hooking PAM, you can backdoor SSH, you can backdoor SU. So you've got like some families only really implement the accept hook, where like if there's a magic source port, it'll drop you a root shell instead of giving you like a web page or whatever when you connect to the web server. Others will hook PAM. There's some other examples by a guy called Hombre that hook write, and if the write call is called with a magic string, for example, like an SSH login with magic string as the username, when that gets written to syslog, it'll then use that to trigger and set a shell. The original first version of Jinx just had port knocking with magic packets. If like certain packets, certain payload data was sent, it'd send back a reverse shell. There are some examples that every time like PS is called or every time LS is called, it spawns a reverse shell. But the coolest ones, the ones that I've kind of seen recently, have been where they hot swap etc password or etc shadow at runtime. So every time a file tries to open like etc password, it replaces it with its own version of it that has like an extra backdoor user in it. And it checks that like it'll only do this hot swapping if it's being called by the SSH daemon. Or similarly, hot swapping the authorized key files at runtime. So like when somebody tries log in with an SSH key, it will add and remove an SSH key like within a fraction of a second. Like there's a lot of potential for more. Like basically, if you can get an input remotely, some kind of way to trigger, you can come up with like a pretty simple remote backdoor that can be done as an LD preload kit. So when I was thinking about remote backdoors and looking at some examples, I thought to myself, what if sometimes the rootkit didn't work as planned? What if I could scan for them? So previously, when I was researching a rootkit called libmdma, I found a copy of it just by Googling strings from it, and I found that like it had been uploaded somewhere in some directory of some previously owned box. And then I realized that if you try LD preload a library that's the wrong architecture or something, you get like a very specific linker error message. So I went to Shodan and I decided to put in like some of the error messages so the dynamic linker will shit out when it's having like a bad day. And what we find is all of these. And what these are telnet log, like if you connect to telnet on any of these systems, it spits out this object cannot be preloaded, cannot open shared object file. And it's like the linker on those boxes is busy desperately trying to load this library that doesn't work. So it spits out this error, and you know that box has been done by somebody, and they put a piece of malware called libsystem.so on it. So I googled the error message, and I found on the forum of the vendor that makes those NASs, there was like, people were like, hey, my NAS is broken, it's giving me this error, and the admins of like the NAS company didn't seem to twig this is a malware infection. They were like, oh, just delete the file, it'll be fine. Just pretend nothing happened. I found more references to it on some Chinese web forums, and they're like, oh, here's the fix to like make it go away is just, deleting the file by echoing into it. Again, it's etc libsystem. And it seems that this particular malware infection was like quite widespread because it was absolutely hosing people's boxes. So whoever had written it had clearly fucked up somehow, and their rootkit didn't actually work. So when I looked a bit further, it turns out that this had been previously noted by Trend Micro and Sandfly, and the TLDR is a group called Kinsing. We're dropping a modified Bjork rootkits. They could hide their crypto mining and other shenanigans activities, and it didn't work because they compiled it wrong. So it just absolutely hosed all these systems they were trying to put it on. Like anything you do, like even if you managed to get a shell working on one of those things, all you get was like output errors for days. Every single time I tried to call anything, it was just broke. So I recently started working trying to categorize these, because there's so many of them in the wild, but the actual diversity of code is pretty small, because they're all based on each other, like, kind of like pedigree dogs or something, you know? There's like, they're all like the same 3 or 4, like, lineages. So, when I started trying to figure out a way to categorize and make a worksheet, you would get your sample and you go, what functions does it hook? And then does it reuse code from known rootkits like Jinx? What backdoors does it implement? Does it have any self-protection methods? Some of them get really clever. Like, some of them will load their file into memory and then spit it back out. Like, they will, if they detect somebody try to delete one of the rootkit's files, they'll just move the file instead. And they do some pretty neat stuff. Like, do they do string obfuscation? And also, how does it decide what stuff to hide? So most of them use magic GIDs, like where the group ID of a file is like 1337, and that file is hidden. Some others written by somebody, guy wrote Vlaney, used XAtters, which extended attributes, which I thought was really cool. So I started out, and still a work in progress, but I think the best way to categorize these is going to be an Excel worksheet. And that makes me want to, not do this anymore. So for the what functions as a hook, I do have the spreadsheet. I'll be uploading it later. I picked a few example rootkits and basically made a list of every hook they implement. And some of them only implement like 10 hooks, and some of them like, what I think it was Umbreon, implements like 100 different hooks. Like, somebody sat down and went, fuck it, I'm writing a backdoor for every single function in like the glibc. It took ages. I still need a couple of friends of mine to go over and make sure I haven't missed anything. Vlaney also took a billion years to go through, but at least whoever wrote that one put like all the names of the hooks in one file so I could like actually read it and not want to, so that's one way of categorizing them. Another way of categorizing them is like, does it implement a remote backdoor or a local backdoor? What backdoor does it implement? And does it implement one that they've copy and pasted from Jinx? Because most of the time, yes. If it's an accept hook using SSL, it's pretty much always going to be a Jinx-based kit. That's kind of where we're at the moment with categorizing them. The spreadsheet would go here so you can stare at like libc names, but it'll be up on GitHub probably tomorrow. And then, so the bit that I've been getting to is like what the future of this holds, and this is something that I've noticed only over the last like 6 months when researching some of these again, is task-specific rootkits. So previously, all the rootkits these guys were using were like very generic, just like giving access. But recently, I came across a sample called libcurl deflected by Sandfly, and the whole rootkit is designed around hiding a Monero miner, rather. And all this rootkit does, it basically ensures that miner is hidden. So like it hides like how much system resource utilization is being used. It hides like the miner's process, it hides the miner's network connections. Its one job is to make sure they keep like wasting somebody else's precious clock cycles mining shitcoins for the next like however many years. And there's also been a couple of POCs for hiding containers. I know the Vlaney rootkit does. It's got a thing for creating like a hidden LXC container in it, which I thought was really cool. And I think that's kind of going to be the future of these, because everything's containerized now. We're all moving like Docker and Kubernetes and all that other hipster nonsense. And like, we're now seeing rootkits that are specific to those environments to like create a hidden container, hide the container, and like now you've got infrastructure in your infrastructure that you can't see, which I think is kind of cool. There's also some other cool tricks that I've seen, like people using them to break SSL to get around certificate pinning in Android apps, using the exact same technique to kill the SSL thing. That's kind of where it's going in future. That's kind of where the cool cutting edge of it is. And the cool thing is, most of these seem to evade EDR on Linux, because I don't know why. I guess the EDR companies they keep compiling things dynamically, so like the rootkit affects them. So it's really weird. Sandfly were like claiming that libcurl evades like pretty much all the major Linux EDRs. I think there's definitely some stuff there. I do have a ton of references that will all be in the Git repo as well when I make it public tomorrow. These are like a small sample of them. I've got references, code samples, all that good stuff. So yeah. Any questions?
Beyond component study, is there anything that you can do to protect most suited libraries that, or is there any other setting, say, don't like suited libraries that across the freedom settings, or what mitigations are there?
So mitigation-wise, there isn't actually much for some weird reason. This is something that has been talked about quite a bit recently. Statically linking everything is one way, because that just kills that entire category of kits.
A million.
Yeah, you end up with a lot of file size bloat. There is the interesting is I couldn't figure out a way to configure glibc to not load to not allow preloading. Now I know that if you use muscle instead, musclibc doesn't allow system-wide preloading, but glibc does. So there could be something there, but the mitigation-wise, it's one of those features that's in Linux that nobody really thought through, because it's literally the insert rootkit feature,
Yeah, so to that actually, so news another thing about things much more unsafe variables on linking to set US boundaries. So it's something that you might have seen Rootkit, Rootkit exploit. One of the POCs is using the deep version.
Mm-hmm.
That's one of those unsafe variables that we think and LD preload is another one. So because it's in the safe execution context, it will clean out. So I'm not sure if you just of BSD. I don't know since when they started doing this. So that's one of the mitigations.
Cleaning the end. That makes sense.
Yeah.
Yeah, that's... Yeah?
You see any kernel EDR
So EDR in kernel? I actually haven't seen anybody write one that works on Linux properly. Because, again, you're writing a rootkit for Linux, if you're writing an EDR, there's functionally no difference between the EDR product and a rootkit. And maintaining kernel modules on Linux it's a ball ache. You're just looking at pain and suffering. Yeah, step one, don't get owned. Disconnect that. Oh good, it actually works.